described as a measure of quantity of matter. In short, you are asking how many particles are there in a particular substance. So when you're talking of measure of quantity of matter, now you're talking about mass. But on the other hand, weight is not a measure of quantity of matter, but it has to do with the force that is exerted by the earth on a body. So this is the gravitational pull of the body by earth. This means that if there is no gravitational pull, then a body will have no weight. When you go to the moon, since the pull really reduces, you'll find that people weigh much less on the moon surface than they weigh here on Earth. Difference number 2 has to do with the units, the SI units. So for mass, the SI unit is kilogram. We use kilograms as an SI unit. SI means System International, or the internationally recognized standard unit. Now for mass is kilogram, but for weight, SI unit is the Newton, or N in short. Then number 3, we have something like 5 differences. Difference number 3 has to do with the instruments that are used to measure mass and weight. So instrument to measure. Here for mass, we use the beam balance. Perhaps you've someday gone maybe to a supermarket or maybe to a shop or even a butchery, and you want to be given a half a kilogram. So what they use there to measure that is actually a beam balance. But we also have in the physics lab beam balances. But for weight, we do not use a beam balance. We use what we call a spring balance. Usually it has a spring, so somebody just suspends it in air, and then you see how much the solid or the body has pulled the spring balance. In markets, some markets, sometimes you want to buy a cabbage, sometimes they use a spring balance to help you or to sell you the cabbage. Number 4, difference number 4 has to do with the changes. Mass never changes. When you take mass, say 2 kilograms to the moon, it will still remain 2 kilograms, or even to any other planet, it remains 2 kilograms. Or all parts of the earth, the mass will still be 2 kilograms if you had weighed it and it was 2 kilograms. So mass does not change. With geographical positions or locations. But on the other hand, weight changes. With geographical positions or locations. Even on this earth, there are places, you see that our earth is not a perfect sphere. So there are places, say on the North Pole, where the surface of the earth is nearer the center of the earth than say in the equator. So when you have such because usually the gravitational pull has to do also with how close are you to the center of the earth. So you'll find that the weight at the poles is not exactly the same as the weight at the equator. So weight changes with the geographical location. Then the final difference that we have is we say mass is a scalar quantity. Some people pronounce it as scalar quantity. Mass is a scalar quantity. What we call a scalar quantity or scalar quantity is a quantity that has only magnitude. It does not have directions. So mass, when you talk of mass, really you don't get the idea of direction. But when you talk of velocity, that now is a quantity, but also it's got direction, or force even. Force, you can ask, how much force did he use on you? And which way did he push you? So force has got both direction and magnitude, but mass does not have direction. So mass and weight, they differ in that weight is what we call a vector quantity. So a vector quantity has both magnitude and direction. A scalar quantity, we say, has only magnitude. So these are the 5 differences that we can cite between mass and weight, so that you do not confuse the 2 quantities. I will now proceed to say something more and discuss the relationship between mass and weight. And this is now a mathematical relationship. So relationship between mass and weight. Now, that relationship is given in form of a mathematical relation, and this mathematical relation is simplified as W is equal to mg, where W is weight, m is mass, and g is a constant. Is a constant that we call a gravitational constant. On Earth, the value of g is given as 10 Newton per kilogram, or when you're using it in motion, the units can also be given as 10 meters per second squared. It's not a very accurate value. Some people would give it as 9.8 or 9.8 something, but usually for simplification of our calculation, we just call it 10. So now, how do you use this relationship? What this relationship means on Earth, for every 1 kilogram, of a mass, there is a pull on it on Earth, and that pull is equivalent to 10 newtons. Now, if you have 2 kilograms mass, on the other hand, it will have a pull of 20 newtons. So that means that for every 1 kilogram, there's a 10 newtons pull. If you have 3 kilograms, it now experiences a 30 newtons pull. So that means if you want to find the weight of a particular body whose mass you have been given, all you need to do is just to use this equation. So say if somebody weighs 600 newtons, what is the mass? So this is the weight. Weight is equal to 600 newtons. So how do you find mass? From the equation above there, you get mass by dividing weight by g. So it's going to be 600 newtons divided by 10 newtons per kilogram. The newtons are going to cancel, so that will give us 60 kilograms. So that is how you are able to relate the mass and the weight. I want to give one final problem that we will find very common tested in secondary schools. Problem. A body has a mass of 55 kilograms on Earth. What would be its weight on the moon, where the gravitational constant or gravitational field strength is 1/6 of the Earth. So we are now being asked about the weight on the moon. So we can say weight, and I'm going to give it a small suffix here, m, to mean this is the weight on the moon, is going to be the mass times the gravitational field strength of the moon. Now, the mass remains the same. We have said that mass never changes. So the mass, since it was 55 kilograms on Earth, it's still going to be 55 kilograms on the moon. But now what has changed is the gravitational field strength of the moon. For Earth, we know it is 10, but now the moon is 1/6. So we are going to say times 1/6 of the gravitational field strength of the Earth, which is 10 newtons per kilogram. So you will have to work out 55 times 10/6. And that one, when you work out it's going to be 550/6. So when you work out, it's going now to give you the weight on the moon. And whatever value you're going to get here, I'd want you to work it out yourself, but whatever value you're going to get it out is going to be in newtons. So those are the kind of questions that you are tested in. It may come in different. Sometimes you may be given the mass, or sometimes you're given the weight, and then you're supposed to find the mass. So you just always use this relation W is equal to mg. Thank you very much.